This is the final video for chapter 6. Section 6.6 is the theorem of limits, and this is self-study, so you can read through it on your own time. Section 6.7 moves on to continuity and differentiability of function. For a function to be continuous, we must test three elements. First, the point n must be in the domain of the function. That means g of n must be defined. Second, the function must have a limit as v approaches n, or the limit vn of function gv exists. And for this, we need to test it from left and right. The limit, and then finally we need to test that the limit is equal to the value at gn. So the limit equal to the value of gn. So if we take an example, we have the function q equal gv, and it is equal to 4 minus v squared over v. So is this continuous over the domain? What that asks is, can you think of a point where this function will be undefined? In this case, if v is equal to 0, the function q is undefined. Therefore, gv equal to g of 0 does not exist. And therefore, rule 1 fails, and the function q is not continuous over the domain. The domain in most cases is the value, all real value. If we take another example, q equal to v squared plus 2v plus 4. So our first rule, if we take any value of real numbers, there exists a value. So there exists a value for any n. Secondly, the limit as v approaches 4 or any other value, so q4 is equal to 4 squared plus 2 times 4 plus 4, which is equal to 28. So the limit exists. And third, the limit is equal to the value of the function, and therefore the function is continuous over the domain. Sometimes it's easier to understand continuity if you see a discontinuous function. So for example, if we have a function like this, where it says f of x is equal to -2 if x is smaller than 0, and it is equal to +2 if x is larger than 0, larger equal to 0. So larger equal to 0 is a dot, and this will be an open circle. Let me just indicate that better. And an open circle. So if we want to test our first rule for this function, our first rule is n must be in the domain of the function. So yes, there's all values of n is defined. Why is this the case? Because even for x equal to 0, we have the value of 2. But the limit as x approaches 0 from the left is equal to -2, because we're in this domain. So from the left, from negative values, it approaches -2. And the limit as x approaches 0 from the right hand side, from positive values, it is equal to +2. So the limit exists. But the limit is not equal to the value of the function. So if we are very close to the 0 line, we don't know if we're -2 or +2. And that's why the limit is not equal to the value of the function at 0. Therefore, the third rule fails and the function is not continuous. For differentiability, we are not concerned with the function as it is, but we are concerned with the slope of the function, or if the difference quotient exists. So our continuity condition says that the limit as x approaches x0 of the function fx is equal to f of x0. The differentiability condition, or the differentiable condition, states that the slope at x0 must be equal to the limit as delta x approaches 0 of our difference quotient. To explain this, let's look at the absolute function. So y is f of x, and this is equal to the absolute value of x. If we look at this graphically, we know that if x is equal to 0, y is equal to 0. So we have that point. If x is equal to 1, y is equal to 1. So on our right hand side, this will be a positive slope. If x is equal to minus 1, y will be equal to minus 1, which means we have a negative slope from the negative side. So if we approach from the right hand side to 0, our limit will be equal to 1. If we approach from the left hand side, our slope will be equal to negative 1. What happens at 0, we're not sure. There's no tangent line at 0. And because there's no tangent line, the function is not differentiable. If a function is both continuous and differentiable, it is said to be continuously differentiable. And we denote this by C1, which means it is continuous differentiable. Another thing to note is that differentiability is a sufficient condition for continuity. So if we know that a function is differentiable, we also know that the function is continuous.